Welcome back to the Hydraulic Lab 1 Part 2. Here we are going to talk about flow measurement devices such as ventrimeter, orifice plate and volumetric area, which in the experimental part, which is the next session, or Lab 1 Part 3, we are going to do that experiment, and now we are talking about their structure and their analysis here first. So ventrimeter, orifice plate and volumetric area are three set of devices to measure the pressure difference, total head loss and also discharge. Here, for example, assume a ventrimeter. As the flow comes in to the cross-sectional area 1, this is the flow direction, we have velocity 1, and it just passes through a narrow area which we call it throat or the neck, which we squeeze the water in a smaller area, hence velocity increases. We call it V2 and area 2. Within this distance, then we measure the head loss. If we want to know how it works in terms of Bernoulli equation, Z1 plus P1 over gamma plus V1 to the power of 2 over 2G, three components of Bernoulli equation at the cross-sectional area 1 should exactly be equal to cross-sectional area component of Bernoulli equation in cross-sectional area 2, here excluding head loss. For ventrimeter, for the first one, if you look at continuity equation, you can see discharge is all the time the same. Discharge passes through the ventrimeter from any cross-sectional area. So Q is equal to area 1 times velocity 1 is equal to area 2 times velocity 2, and blah blah so on. Area whatever you have times velocity of that cross-section. So discharges remains the same. And but velocity for different cross-sectional area changes. So V1 is the same amount of discharge divided by area 1, and velocity of cross-sectional 2 would be the same discharge divided by A2. As you can see here, in cross-sectional area 2, area decreases. So diameter decreases, area decreases. So with the same constant discharge, velocity should be increased. So in terms of Bernoulli equation, velocity is increasing in the cross-sectional area 2. 2. First of all, because we are measuring both velocity from the same base and at the same elevation, Z1 is equal to Z2. So these terms are cancelling out. So we don't have elevation term anymore for two sides. So it just simplifies to, let me rewrite the equation here once more. So P1 over gamma plus V1 to the power of 2 over 2G would be equal to pressure P2 over gamma plus velocity 2 to the power of 2 over 2G. As we see here in cross-sectional area 2, area drops, hence velocity increases. So velocity increases because the whole term should be equal to the first part. As velocity increases, something should be decreased to compensate. Gamma and G are constant, so pressure in the cross-sectional area of 2 drops. Similarly, in cross-sectional area 1, area is higher. If it moves from 2 to 1, area increases, so velocity drops. So velocity drops. To compensate the second part, pressure should increase. So one can say in venturi meter, in cross-sectional area, we have lower velocity and higher pressure, while in cross-sectional area 2 we do have cross-sectional area 2 we have higher velocity and lower pressure. The same concepts apply for orifice plate, second apparatus. The difference between venturi meter and orifice plate is that in venturi meter change of area occurs in a relatively smooth, longer distance. So it's a gradual change or drop. But in orifice plate, just assume this is the inner hole in orifice plate. This is orifice plate. Then you look at it from outside, and this is a smaller hole inside the orifice plate where it just narrow the flow very sharply. So in terms of head loss, the pressure difference in orifice plate occurs very suddenly and sharply. So we expect to see a higher drop in orifice plate in comparison to venturi meter, where there is a smooth change of area, not a sudden one. So head loss is should be lower. In part 3, next part, we are going to work with the experimental setup for venturi meter, orifice plate, and volumetric area. See you.